Okay, so here we go again. Analysis of variance is abbreviated ANOVA. The long name, if you will, is analysis of variance. We get the name ANOVA from the first few letters of each word. You take AN from analysis, the O from of, and the VA from variance, and you get ANOVA. It's just kind of the shorthand, so that's where it comes from. ANOVA, we've looked at, and let me summarize them for you, and I'll do that on a piece of paper over here so you'll kind of can have them all together at some point for the final. We have thus far talked about the one mean z-test, which is applicable to quantitative data, which means you would have numbers specifically related to the mean of the population, which is mu, and we use the normal distribution. And it's upside down. See if I can fix that. Okay, that was in Module 3. Then also in Module 3, we talked about the one mean t-test. It is also used when you have quantitative or numerical data. And again, it's a question about the mean of the population, but you do not know the population standard deviation. Remember, that's the difference as you get ready to take your Module 3 exam. That's the difference between the two. Z, you know the population standard deviation. With T, you don't. And we use the student's T distribution. Last week, we talked about chi-square, specifically chi-square goodness of fit. It's one of the few statistical analyses used with qualitative data. So we had words or phrases. And we were looking at how well our data fit the stated distribution. And primarily it talks about that in terms of proportions, if you want to think about it from that perspective. And we used the chi-square distribution. So today we're going to add another one to that. Okay, so today we're going to add analysis of variance, or abbreviated ANOVA. And I'll come back and put in the details for you there, or you can catch them as we go through It's PowerPoint. The difference between ANOVA and some of the others is this. ANOVA is quantitative data that has been sorted into groups by a qualitative variable. Okay, so it's kind of a combination of the two, because you're going to have numbers that are sorted into groups by some word or phrase, by some category. So for example, it might be, the question might be, is there a difference, in the mean drive-through wait times at the 3 McDonald's locations in Cartersville, Georgia? Okay, there's probably more than 3, but I know of 3. Okay, so we're looking at wait times. So time would be a number, but we're sorting it by location. So you would have location 1, location 2, location 3. Another example, is there a difference in the mean GPAs for the different pathways at Georgia Highlands, or the different majors? So we could look at the averages, the means for GPAs for students who are in education, nursing, dental hygiene, business, psychology. We could look at all the different pathways and see, is there a difference between those? And notice the way the question is worded. That's the other thing that we're looking for when we're using ANOVA, is we're looking to see, are the means or the averages the same, or are they different? So the question is usually worded in a manner similar to what I have here, where it says, is there a difference? Or it could say, is there no difference? I've tried to turn the air down, so we'll see. Okay. In the mean commute times in 3 different cities. So if we took, say, Atlanta, Chicago, and LA, and we looked at the mean commute times for people. Again, time would be a number, which is quantitative, and the city is a word, which is qualitative. So again, as I just mentioned, ANOVA is a test to determine if there is a statistically significant difference in the means among 3 or more groups. Okay, that's one of the keys related to ANOVA. Typically, ANOVA involves at least 3 groups. You could have 100 groups, but the minimum is 3. And we kind of skipped over, we went from talking about the one mean z-test, which we were talking about 1, and now we're talking about 3 or more. So you may think Miss Ralston can't count because I skipped 2. There's actually a test, it's actually a different z-test or a different t-test that you can do with 2, where you can compare 2 different means and talk about whether mean 1 is equal to mean 2 or less than or greater than. We didn't do that. 1, we didn't have time. But once you know how to do the one mean test that we've already done, transitioning to that 2 is easy. It's also a topic that will be discussed in the next course, which is Math 2401. But so we kind of skip over, because remember, this is a survey course, and we're trying to hit a lot of different topics. And more times than not, you're probably going to have more than just 2 groups, so you're probably going to have at least 3. So that's when you want to apply ANOVA. Kind of what goes on behind the scenes, again, is we look at the variances. Remember, variance is how different the values are among themselves or between different data sets. We could also talk about it in terms of standard deviation. Most times we talk about it, in this case, in terms of variance. Remember, because variance, remember we talked about way back when, that variance was that unbiased estimator. It was on target every time. So that's why they're using the variance. to help us determine if our means are the same or if they're different. Now, again, it's obvious when you look at the means and you can see, well, Ms. Ralston, they're all three different numbers, so they got to be different. But again, it's not just the fact that they're different. It's, are they statistically different? Are they different enough from each other for us to say, yeah, there's something going on? The distribution that we use for ANOVA, well, let me tell you what the assumptions are first, okay? There are 5 basic assumptions that we make. You really don't need to know these. You don't have to write them down. I'll post this video. But again, these are things that are going on behind the scenes. And if you were doing this in the real world from scratch, you know, you were doing your own research, you'd want to verify these things. For us, these assumptions are in place, just so you know what they are. Each population from which a sample is taken is to be assumed to be normal. So we assume that our big picture focus, the population is normal, and we're going to draw our subsets from that normal distribution. All the samples are randomly selected, so one of our sampling techniques that we've talked about previously are used to do it. And they're also independent. Now, independent means that basically you're not going to put the same people or the same things back in there again. Once you draw that sample is set. You're not going to throw them back into the mix so that it doesn't affect what you select the first time is not affected by the second time, the third time, the fourth time. That's what independent means. The populations, again, we've assumed they're normal, but we're also going to assume that they have equal standard deviations or equal variances. And then what they call the factor is the qualitative variable, and the response is the quantitative. Now, those are just fancy words, okay? And it's how it's labeled in Minitab and a bunch of your statistical software. But again, we're not going to get so caught up in all of that language. Now, the ANOVA is based on a different distribution. We've talked about normal, we've talked about student T, we talked about chi-square. Now we're going to talk about F. The F distribution is named after an English statistician named Sir Ronald Fisher. And he's kind of one of the, if you want to think about it, one of the big dogs in statistics. Okay, he did a lot of stuff in statistics. It's just one of them, but it's named in his honor. So it's called the F distribution in honor of Sir Ronald Fisher. Notice in this diagram that I have here in the corner, this is one of the F distributions. Again, there are an infinite number dependent upon the degrees of freedom, and we'll talk about that in just a minute. But again, notice, like chi-squared, it is not symmetric. Notice how you have this hump on the left-hand side, and when it's humped on the left, it's skewed to the right. So the F distribution, like chi-squared, is skewed right. Okay? The consequence of that, remember, is that because it is skewed to the right, your test statistic that you calculate for F and ultimately for the ANOVA will always be 0 or positive. It'll never be negative. Okay, because the distribution is skewed to the right, your test statistic will always be 0 or positive. It will never, ever be negative. The F distribution, its shape is actually determined by 2 different degrees of freedom. We're going to see in a minute that the F test statistic is a ratio or a fraction. And so it's looking at 2 different things. It looks at how different the values are from group to group, so between the groups, that gives us the degrees of freedom for the numerator of the fraction, and it's between the groups. But then we also look at how different are the values within the group. Okay, that's the denominator. So we're looking at the relationship between a comparison of the groups from group to group, but also a comparison within the group. So you have two different degrees of freedom. I don't know if you can see it, but on this graph, it says F distribution, parenthesis, 5, 10. That 5, 10, 5 tells me that we had 5 degrees of freedom between the groups and 10 degrees of freedom within the groups. Now, I'm going to show you how to calculate those because Minitab's going to do it for you. Okay, so we don't have to get worried about that. The other thing that I mentioned it with chi-square, as your degrees of freedom go up for either the numerator or denominator or both, as they go up, our F distribution begins to approximate the normal. Okay, so the higher your degrees of freedom, this shape becomes more normal. I think I looked yesterday, I was looking at some of these, and I believe it when it gets to about 40. When you have about 40 degrees of freedom is kind of when it starts looking normal. But don't quote me on that. Okay, so we calculate the F test statistic. And again, it's a ratio, it's a fraction. The true definition of the F test statistic is you calculate, we're going to let Minitab do it for us, but we calculate the mean square between the groups and we divide it by the mean square within the groups. Now guys, we are not going to do any of this by hand because the amount of math that has to be done to calculate the F-test statistic is unreal. If you were to look at your textbook, I don't recommend it, but it takes about 4 pages of the textbook to explain all of the calculations that go into this. It's about, if you were doing it by hand, it's about 6 pre-calculations before you can ever get to figuring the F. Okay? Do not attempt to calculate the F-test statistic by hand. Nobody in their right mind would do that since we have the technology to do it. So we're going to let Minitab do the work. Now, Minitab's going to give you lots and lots of results and tell you lots and lots of different things. And that's great, but again, we're going to focus on one small piece. Again, because we're skimming the surface, we're getting an introduction to ANOVA. We're actually going to do the simplest type called one way. We're only you can take your groups and sort them maybe by 2 different variables or 3 different variables. Okay, we're only going to do it with one. Remember, sometimes we have those fancy-dancy notations. The fancy-dancy notation here is that our variable x approximates the F, and then you have the 2 numbers in the parentheses. The first one is the degrees of freedom for your numerator, which is between the groups, and then your degrees of freedom for your denominator, which is within the groups. And again, that's just a notation you might see. Sometimes you'll see that written like into reports and things when you're reviewing them. Okay, so we've got a new distribution, new process. Not really hard. We're still going to use those 6 steps of hypothesis testing. Stating the hypotheses, identifying the information we need, deciding that we're going to do ANOVA, calculating it using Minitab, making our decision and writing our conclusion. Those steps are not going to change. Okay? So let's see if we can dive in to an example. These problems are usually, again, sort of similar to what we've done, but with chi-squared, it looked like we were usually given a table. You'll also usually get a table for ANOVA as well. And this one's labeled number 2, but we're going to do it as number 1. It kind of goes back to one of the examples I gave you in the beginning. It says 3 random samples of times in minutes that commuters are stuck in traffic are shown. At alpha equals 0.05, is there a difference in the mean times among the 3 cities? And in this particular example, we looked at Atlanta, Boston, and Detroit. Okay? So we've collected our data. And again, typically with ANOVA, it'll be presented in a table form. Again, remember, you're going to have numbers sorted into groups. So I have my times, and they're sorted into groups. And in this case, my groups are the cities. So even before we begin or do anything else, it may be that you can recognize, oh, this is going to be an ANOVA. Now, usually we wait a little bit. That's usually step 3. But again, when you read the problem and you realize, oh, I've got quantitative sorted by qualitative, that's ANOVA. Okay, I'll make us a note here that this is quantitative sorted by qualitative. We have times sorted by cities. Typically, our first step is to identify our hypothesis. And usually we want to look for, those things like claim, conclude, believe, think. Again, with ANOVA, it's usually worded this way. Is there a difference in the mean times among the 3 cities? Mathematically, when you think of the word difference, what does it mean to you? Would it mean, say, equal, not equal, less than, greater than? Difference? Okay, it could be less than or greater than. Mathematically, the way we show less than or greater than is that it is not equal. And so if this is not equal, is that going to be the null or the alternative? It is the alternative. Okay, so here's how we write it. Our first step, as is always the case, we want to state our null hypothesis and our alternative hypothesis. We could just about use the sentence that's written there with just a little bit of a few extra words. Okay, we would say at least one mean commute time differs among the 3 cities. Okay, a couple of things here. The statement says, if we change it to a statement, would say there is a difference. But we have to add this little caveat that at least one, because it only takes one being different to make them not all the same. Okay, so every hypothesis, alternative hypothesis related to ANOVA should begin with that phrase, at least one mean, whatever, differs. Okay, that's pretty much how it's going to be worded. At least one mean of whatever differs. And again, mathematically, that implies that this is not equal. Now, the way you word your null hypothesis is we would say, well, there's different ways you could say it. You could say all mean commute times are approximately equal. You could say there is no difference in mean commute times among the three cities. Again, there's other ways you could say it, but the thing is, the null hypothesis should always imply equal. So with ANOVA, just like with chi-square goodness of fit, okay, your null hypothesis, however it is stated, should always imply equal. And your alternative hypothesis, regardless of how it is stated, should imply not equal. Step 2 is usually to identify the information that we need in order to calculate the test statistic. We need our sample data information. Well, our sample data information has already been summarized for us in the table. And the only other thing we need, of course, is our level of significance. Okay, so we have our table and we have our level of significance, which is 0.05. Remember, if the level of significance is 0.05, that my confidence level is 95%. Remember the connection. We've already decided, at least initially, that we're going to do ANOVA. Again, recognizing that we had numbers sorted into categories, and also the phrasing of the hypothesis. Is there a difference? Lets me know that I'm going to do ANOVA. So then I'm going to go out to Minitab to calculate this. Okay, so I'm going to kind of give you the steps. The first thing you have to do in Minitab is enter the data, which is in that table. Okay, in column 1, you'll put Atlanta. In column 2, you're going to put Boston. And in column 3, you're going to put Detroit. You put each category, oops, spelled that wrong, in a different column, okay? You put each category in a different column. So I'm going to go out and I'm going to do that first off before I tell you the other keystrokes. So I'm in Minitab. Okay, so for column 1, I'm going to enter the date, the numbers for Atlanta. So I'm going to label it Atlanta. For Atlanta, we had 59, 62, 58, 63, and 61. Then I go back to column 2. I put in, label it Boston. That was the second category. I have 54, 52, 55, 58, 53. Then I have my third category, which is Detroit, and I enter 53, 56, 54, 49, and 52. Okay, so I have all of the data. The table is entered. Okay, and I'll write these down for you in just a minute. Then we're going to go to Stat, and we choose ANOVA specifically one way. So let me write this down on the paper and then you can copy it. You go to Stat, ANOVA, one way. Stat, ANOVA, one way. The wizard comes up. Okay. We need to change this option to response data are in separate columns for each factor level. Okay. That's the way I'm having you do it. I'm having you put each category, remember those are called factors, in a different column. So you want to change that selection to response data are in a separate column for each factor level. And again, that's how I'm going to have you do it every time. Then we click in the box labeled responses, and I have to tell it where the data is located. And I have to tell it about all of the data. So I'm going to choose Atlanta, Boston, and Detroit. You should have all three of those in the responses. Okay, so that's the next step. After you've done that, then we're going to choose all responses. Then we have to go to options. With options, you want to assume equal variances. So if that box is not checked, okay, you want to check the box, assume equal variances. Remember, that was one of the conditions or assumptions we were making. You have to choose your confidence level, and it will always be two-sided. Okay. So we had 5% for level of significance, so that means a 95% confidence level, and it's always two-sided. I'm going to tell it okay, and then I'm going to click OK again, guys, and we're going to see lots and lots of results. Don't panic. Okay, when it gives you the results, it really gives you the method. Okay. One thing here is you can kind of confirm your hypotheses. They simplify it. All means are equal. They're not all equal. We did alpha equals 0.05. I mean, it just gives us lots and lots and lots of information. Okay. Really what you need is this third row, the header analysis of variance. The results are presented in a table, and it's calculated your degrees of freedom and all that. What you really need is this F value and its corresponding P value. Please don't get all caught up in all these other numbers. I mean, they tell us some things if we were going further, okay? But we're not. All you really need is under the header, analysis of variance, you need the F value and you need the P value. So I'm going to write that down on my paper. My F test statistic is 15.62 and my P value is 0.000. So basically it's 0. Okay, so let me go back over here for just a minute. And if you want to write down those steps, if you weren't able to write them down as I was speaking, okay, so you have to enter the data. Once you have your data entered, you go to Stat, ANOVA one way. Change it to response data are in a separate column for each factor. Choose all your responses. And then under options, you have to assume equal variances, select your confidence level, and it will always be two-sided. Did you get it, Chow? Okay, so then after we've written down our F test statistic and our p-value, we're ready to make a decision. And guys, it's the same decisions that we've done before. We have to compare the p-value to the level of significance. So I have basically 0 compared to 0.05. Okay, same comparison that we've been doing since we started hypothesis testing. It hasn't changed. So if I compare this, 0 to 0, there's no difference. 0 compared to 5, 0 is less than 5. So P is less than or equal to alpha. When P is less than or equal to alpha, you reject the null. That guideline hasn't changed. It's not going to change. When P is less than alpha, we always reject the null. Now, what that means in the context of our problem, if we reject the null, remember that means that the null is false. So we ultimately are concluding that there is a difference because the false statement is there's no difference, which means the true statement would be there is. So then the last thing that we do, it's always the last step, is we state our conclusion. We would say, at alpha equals 0.05, there is a difference in the mean time that commuters are stuck in traffic among the 3 cities. Okay, there is a difference. Now, again, as we talked about before with chi-square, this tells us there's a difference. It doesn't necessarily tell me which one is different. Now, some of these other numbers could tell me they were different. The other thing that might help me to look at, and again, you're not expected to do this, but if you look at this graph here, okay, this graph shows the mean is the dot, and then the lines out from it is your confidence intervals. See how Boston and Detroit overlap? So they kind of have some, they're kind of in common. But see how Atlanta, it doesn't overlap. It might overlap a little bit with Boston, but I doubt it. Okay, so just this graph here gives me an idea that Atlanta is probably the one that's different. Okay, but I'm not going to statistically prove that. Okay, we're not going that far. Okay, all we're going to prove is that there is a difference. Now, again, in real life, we might continue on, but because of the nature of this course, we can't do that. Everybody okay? All right, let's look at one more. Let's see. Okay, let's look at this one because it's worded a little bit differently. go back over here where you can see it. Okay. The chest deceleration in a car crash data are given below. Use 0.05 significance level to test, this one even tells you, to test the null hypothesis that the different categories have the same mean. So again, this one's worded a little bit differently. It actually tells you the null hypothesis is that the different categories have the same mean. Now, I hope, should they have not told you that, if they hadn't explicitly said null hypothesis, I hope you realize the word same mathematically would imply equal, which does make this the null. Couple other things I would point out to you. Notice how this particular table is set up. Notice that my categories are down the left-hand side and my numbers are running across. So subcompact is 55, 47, 59, 49, 42. Okay, so you've got to pay attention to how the table of information is set up. But again, I hope you recognize kind of right off the bat that I have categories sorted into chest deceleration. Okay, so this is some value they calculate when they're maybe testing car crash, testing different size cars and using a test dummy. Okay, it's called chest deceleration. So again, hopefully you can recognize right off the bat that you're doing ANOVA, because we have quantitative sorted by qualitative. We have numbers sorted into categories. In this case, the different categories are the size of the car. So our first step, as is the case with any hypothesis test, is to state the null hypothesis and the alternative hypothesis. And they've kind of already told us that what we have is the null. So we would say the different categories of car size have the same mean chest deceleration. Now, I added a few details in there, okay? Again, because the details are important. But that does imply that this is equal because of the word same. Then my alternative, I'm going to say at least one mean chest deceleration differs among the car sizes. Okay, again, I pointed out to you just a minute ago, you're always going to say at least one mean, whatever the mean is, differs, and that implies not equal. Again, you've been given the information. Hopefully you've paid attention. I pointed it out to you how the table is set up, and you need your level of significance, which is 0.05. Remember, if alpha is 0.05, that your confidence level is 95%. I'm going out to Minitab and I'm going to enter these numbers. Now, again, you can start with a clean sheet if you prefer, or I can just go over, and go to a different column. So I'm going to start in column 6. I'm going to have subcompact, and I'm going to enter the numbers: 55, 47, 59, 49, and 42. Now, one other thing I'll point out to you as I'm typing here, I have compact. In each of these two examples, so far, you've had the same number of items in each category. But guys, you don't have to. You don't have to have the same number in each category. You typically will, but you don't have to. It still works the same way. Okay, so I have 57, 57 again, 46, 54, and 51. Then we have mid-size. Notice that the first question we had 3 categories. This time we have 4. I mean, you got to have at least 3, remember, and 45, 53, 49, 51, and 46. And then full size, we have 44, 45, 39, 58, and 44. Okay, so I've entered all of the numbers. Then we go back to stat, ANOVA, one way, response data are in separate columns for each factor level. And then I got to choose all 4 of them: subcompact, compact, mid-sized, and full size. All 4 of them. If you have 10 columns of data, you got to choose all 10. You got to choose all of the columns that are part of that question. Options, assume equal variances, 95% confidence, and it's always 2-sided. Again, you get lots of information, but what I need ultimately is this F value here. And so my F value, or my F test statistic, is 1.34, and the P value is 0.296. So I write it down. Then I'm going to compare P to alpha. P from Minitab is 0.296. Alpha is 0.05. So I'm going to compare it digit for digit. 2 compared to 0. 2 is greater than 0. So P is greater than alpha. When P is greater than alpha, we fail to reject the null. Every time, all the time, when P is greater than alpha, we fail to reject the null. Now, if we fail to reject the null, again, remember what that means. That means that my null is true. Okay, means that my null is true. So when I state my conclusion, I'm going to state it that way. So we would say, at the 0.05 significance level, there are the different categories of car sizes have the same mean chest deceleration. Now, just for comparison purposes, so that you can kind of see, if we look at the graph that mini tab created for this one. Notice how most of those, they overlap. There's not one that's kind of really just way out there like the one for Atlanta was. So again, that kind of supports my idea that they're all the same. Now, if you look just purely at the numbers, they don't appear to all be the same. But remember, we're looking at whether they're statistically significant. So statistically, these all appear to be approximately the same. Just going to look. If you look here at the means, for each one, if you were to round that to the nearest tens, you'd get 50 for each one of them. So that kind of, again, helps me get the idea that they're the same. All right, that's ANOVA. Questions, concerns? Okay. That's it for today. Please remember